So this talk is called Ext4, a case-insensitive Linux file system. This is a new feature we added to the main Linux file system, the one that is the most used by distros today. And actually, we are proposing this feature for a lot of other Linux file systems, in particular Ext4, which already has some part of it implemented. And our next target is probably going to be Btrfs. Anyway, case-insensitive. Case-insensitive in the sense of a file system is basically a file system with the ability to look for file names disregarding case. So any of these files would, any of these lookups, if you search for any of these in your file system, they would all point to the same file, regardless of case. This is very easy for English speakers because, as we all know, the ASCII table, you just flip one bit and you have the uppercase version. So it's a very simple feature to understand what we want to do. And then the question I get asked the most, why? Why do you want to do this? Windows did it, it sucks. Apple did it, it was broken. Why do we want to, is it working? Did it stop working? Yeah, okay. Why do we want to do this on Linux? Linux works very well on the Unix model, which doesn't require case. So why do we want to mess with something that is working? Well, actually, there are very real-world use cases for this. When we are bringing applications from this broken world where they need case, so when we port applications from Windows, when we want to run applications directly that are as they are supported on Windows, so when we are running an application over Wine or Proton, Proton is a framework on top of Wine developed by Valve to run Steam games. So when you want to run Shadow of the Tomb Raider or another AAA game, I just played Beat Saber the other day, on Linux, you can, just using Proton. And all these games, they were written for operating systems that are case-insensitive, and just recompiling them might not be possible. The code is either lost or it's owned by some proprietary company, and you cannot modify the code, or maybe it's open code, it's open source, but it's very hard to change everything. So you want to run these applications. Another very important use case for this feature is Android. Google has taken the design decision of providing the same file system visible in two ways in Android, in two different paths. You can see it either as a case-insensitive file system or as a case-sensitive file system side by side. And this is provided nowadays by a small application, by a small layer called SD-cardfs, which is a bit broken. It has some well-known race conditions that you cannot solve. But they are a very important user of this feature because that's how languages work. When I'm speaking to you, I'm not speaking to you in lowercase or uppercase. Maybe if I'm shouting, but that's not the point. Upper and lowercase obviously makes sense when you're writing, but you don't care. You don't want to need to get the case right when you're doing a Google search. Imagine that I'm looking for a name in Google, and if I don't get the case right, Google won't find my file. This is stupid. And this is what you want in your file system. I want to find my file. I don't care what the name I use it to create. So case-insensitive is actually much more similar to how our day-to-day languages work than making sure you need to get the case right. And in particular, English, case in English is very easy. You can just, as I said, you can just flip a bit on the ASCII table and you get the lowercase version or the uppercase version of any character in the English language. But this is not true for, well, the entire rest of the world. In Portuguese, for example, we have the cedilha, and you cannot flip a bit to go from the lowercase to the uppercase. But it gets even harder. In German, for instance, the uppercase of SS, double S, can be the SZ, which is that symbol over there. But the lowercase of SZ is not lowercase SS. They are different letters. And actually, lowercase and uppercase are not the only two cases. There are languages where you only have one case that is not called lower or upper. There are languages where you have more than one case. So we want to deal with those cases. And the way to deal with that is the thing that everyone loves called Unicode. There's another point. People always say that, oh, case-insensitive is stupid because, dude, we want Unix philosophy, we want the least surprise. Well, the Unix philosophy doesn't really say anything about this. And in fact, if you think about how real languages work, we could go to a bar and discuss that, well, this is the least surprise, but this is my opinion. So easy peasy. In Linux file system nowadays, file names are opaque byte sequences. So they are basically any string null terminated that doesn't contain a slash, forward slash. And if you think about that, what exactly is case when I'm talking about bytes? Oh, if it's just an opaque byte sequence, we are just seeing hexadecimal values, there is no case. Case only makes sense when you're talking about a language. So before defining case folding, we need to define the language we are speaking, and we need to define an encoding. We need to assign meaning to the bytes we are using. That's why when I say about English, I'm talking about ASCII table, because ASCII is what defines meaning to those bytes we are seeing. So you can only have case fold, you can only have case insensitive if you have an encoding. But there are a lot of problems that come from this. For instance, what if I have two files on my file name, on my file system? If my file system is case sensitive, well, hello in uppercase and hello in lowercase are different files. In a case insensitive file system, they are the same. How do I handle that? Which file am I going to return? And finally, performance. Well, comparing opaque byte sequences is very easy. Just do a for loop, compare each byte. You can do a lot of optimizations in that, and you are safe. But when I'm comparing by case, I need to compare with each version of the case for each character and make sure that A is the same, that asset, the German beta, is the same as upper SS or the lowercase ss. And now the Germans, now they created another character which is the uppercase beta, which can convert, which now the lowercase beta can go to the uppercase beta or to SS uppercase or to SS lowercase. So now we have 4 comparisons. Since SS are actually 2 characters, well, you calculate how many comparisons you have just to compare a single file name. And remember that we are talking about file names. It's a very hot path in the kernel. Every time you run ls in your system, you are not only reading everything on your directory, which is a different path, but ls itself, when it loads, it needs to load several libraries that are under user, lib, lib64, blah, 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 .so. Each of these is a name resolution. So if you lose performance here, any program you load in your system is going to take a huge hit. So another question, what are the right semantics for this operation? This is the most controversial thing, because everyone who implemented this did it a different way. Do we want our file system to be entirely case insensitive? Do we want it to be per directory? Do we want the data that we wrote on the disk exactly the exact same case? Is it going to be written like that, or can we do some optimization and store a case folded version already? What if we get it wrong, like Apple did? In 2007, Apple released a new file system called APFS, which was a replacement for the HFS Plus file system, and then decided to not go the data preserving route, which means that you created a file in lowercase and it was converted to uppercase. And that decision broke every iOS system in the world. They had to release an update that just dropped that feature. But come on, guys, it's kernel. We don't want to deal with policy in the kernel. Why not do it in user space? How do we do it in user space? Well, we list all the directory. There is a system call for that, called getDents, which gets everything from the directory. And then we can do all these manipulations in user space. Well, the program doesn't control the directory. Things get created from under the program. The directory changes. So it gets very complicated. It gets really racy. Actually, that's how the Android people tried to solve it at first. And, well, You simply cannot solve it and have good performance at the same time. We don't want to just care about English speakers. Come on, it's 2019. We want Unicode. We want a char set that supports all the world. So let's go Unicode. Okay, Unicode is great for us, the Western people, the West people, but Unicode is actually very bad for Russian speakers. I'll get back to that. And we need to be future compatible. Unicode guarantees that every character is stable, it will never change, but it doesn't say anything about new characters that were intended. So we need to know the specific version of Unicode that we are using for a file system, or our files start to disappear if we update and something starts to collide. So how do we do that? We teach the kernel Unicode. Yeah, people hate me for that, but I did it. So basically, Unicode is a specification of how you interpret of scripts of languages, and each character in any language of the world, from English up to hieroglyphs, they are there. They are assigned a code point, which is a unit of operation. It's not exactly a character because you have code points that can be surrogates or control code points, but basically think of it as a character in any language possible. And it's more than 1 byte, usually. For ASCII stuff, it's compatible, so it's exactly the same ASCII number. But for some more fancy stuff, it can be as long as 4 bytes in the worst case, I think. Yeah, I think 4 bytes for UTF-8. Anyway, we have now over 100,000 code points defined. So we need something that is, we need a table in the kernel that is smart enough to hold 100,000 code points and not mess up with the performance of one of the hottest paths in the kernel. To make our lives worse, remember when I said that you need to compare A with the tilde in uppercase and lowercase? It's way harder than that because Unicode defines this character, but it also defines a composing character, which is just a tilde, and you can combine it with A. And these two needs to be treated the same. To make it worse, there is some very cool things in grammar called ligatures, and you have actually a character that renders to this symbol, FFI, and you have another ligature, FF, and you have the letter I. So you can write FFI as in Office in 3 ways. You can use this character, that character, or those 2 characters, or those 3 characters. And we need to do that very fast. But now I'm only talking about code points. It's translated into byte sequences, and that is what UTF-8, UTF-16, and UTF-32 is. UTF is basically how you represent those code points in a string. UTF-8 is what we are using because it's the most common nowadays. But UTF-8 has a very specific characteristic. It's variable length. So for common letters like A, B, C, D, or English letters in other words, it only takes 1 byte. For Russian letters, it takes up to 4 bytes. So a file written in Russian is 4 times larger than a file written in English, usually. That's why the Russians like other encodings. The people on the East, they use other encodings. Chinese and stuff, they really don't love UTF-8. So it's not fair if I'm talking about internationalization and having a kernel that actually is optimal for everyone in the world. UTF-8 is not the solution. But again, I'm paid by people in the United States. So I support UTF-8. If anyone wants to write another encoding, I have support for that. You're welcome, but I'm not doing it. I'm happy I did it once, never more. So just some very quick definitions. For Unicode, there are 2 main operations. Normalization, which basically is an operation that, given any way to write the same string, A plus tilde, or just A tilde, they all result in the same string. Case-fold is the same thing as that, but for upper and lower case. And there are 2 ways to make normalization. One is the K form and one is the C form. What is the right one? I don't know. it's substring, and I still don't know if I got it right, because they are both stupid. So basically, the k-form do things like this. If I try to normalize the string 2 to the 5, it solves to 25. So basically, if we use that kind of normalization in the kernel and you create a file called 2 to the power of 5, which results to 32. It's 25. Awesome. A stupid form. We're not using that. Let's go to the C1. The C1 doesn't solve ligatures. So if I create a file called as office with one ligature and a file called the office with another ligature, which, by the way, renders the same, they are different files. So it's a mess. Just for instance, the N... What is the name of the export file system that we always use? The NFS, sorry. NFS people chose to use the k-form. Windows people chose to use the k-form. Mac people chose to use the C-form and hack over the ligature stuff. FAT said, screw it, I'm not dealing with internationalization. We case fold A to Z and whatever, the rest is up to you. But for this talk and for the work we did, we, after very long discussions, decided to go with the C-form and make Office and Office different. It's an important decision, but there is no winning solution. For this talk, I'm going to talk about an operation called NF, which is a combination of the N plus F, because I don't care about normalization and I don't want to care about fold. So A plus tilde is the same as A uppercase tilde. Anyway, these are two definitions, and now we have a subsystem. It provides a very high-level API, so you don't need, as a kernel developer, you don't need to care about anything of this. You basically ask for an encoding. You say, I want UTF-8, which is the only one supported, version 12.1, and I want you to convert the string to normalize, and we provide strcomp, strcase-comp, which should be here, but it's not, UCD, case-fold, normalize, and case-folded. We only implemented UTF-8, so now, if you want to have case-fold, you just change your str compare to UCD underscore str compare, right? No, it doesn't work like that. But anyway, just some details on how we built this UTF-8 database, which needs to have a very good performance for this path to work. We auto-generate it on build time. So everything is, we have a huge blob of data that is already massaged, that is already prepared for very fast lookups. So we create a digital forest of a forest of digital trees, which is a prefix tree. You walk on it like you have, the key is going to be the UTF-8 sequence, and the leaves are the characters. If you have a leaf, the character exists. If you are going through an invalid sequence, well, you're going to reach an invalid path, and, well, this character does not exist. And the leaf stores the pre-calculated result of the normalization and the case folding. It's recursive because a character can decompose to one character that decomposes to another character, and we don't want to store all the steps. We just want to go from here to there. And it's cool because it allows very quick lookups to validate characters. So if you create a file with an invalid file name, I know very fast and I can just reject your operation. And the entry of the tree, remember, is a forest. So you have several trees, and the tree that we choose decides the character version. So we have versioning by default. It's a very smart data structure that was invented by someone else. It was actually proposed for this specific implementation was actually proposed by the SGI people in 2014. And they couldn't make it upstream because it was a lot of bike shedding getting this into the kernel, but it was GPL, so we got it in this time. It's all built in during the kernel build, so everything is optimized for you. But it takes like 10 seconds to generate since the database is so big. So we don't build it every time you build a kernel. It's statically. The blob is pushed into Linus tree, and the source files are pushed as well. When we update it, the Unicode maintainer can just go there and regenerate the blob. It doesn't violate GPL because we have the original source codes, but we also provided the blob file, which is basically a bunch of hexadecimal that so you don't need to recompile it every time. It was amazing convincing Linus of that. So the algorithm to generate it, I won't have time, but it's super complicated. I don't want to go into it. Huh? The first version was 90 kilobytes, but there is one script called Hangul, which is used by South Koreans, or North Koreans, I'm not sure right now. And you can do the decomposition algorithmically. So we just removed them from the table and do it as an algorithm, so we could reduce it to like 60K or something. I'm working in trying to make it even smaller, but there is a better solution that makes us not care about size anymore. So now the character lookup works like this. We traverse the tree from the root to a leaf, and then it means that the character, the code point exists. If we want to look for another version, we go to a different tree. If we want to do normalization, we store the normalization pre-calculated in the leaf, and the same for the case fold, so we can implement the NF operator real easily. And this is important. The lookup cost depends on the encoding length, which means that if you are using UTF-8, the lookup of a Russian string takes way longer than the lookup of the English world. So the API looks a bit like this. You just do an UCD load for the version you want, UCD, str, and compare. There is a thin layer on the top that is actually built in the kernel that handles, like, I want to load a different module. If anyone wants to implement any other shard sets, that is more interesting for friends the Chinese. Or you can just load the UTF-8 module that you want, and it will be supported. Unfortunately, the subsystem itself, it's called Unicode. My bad. So if you want to use something that is not Unicode, the name is going to be off. Now we have the infrastructure we want to make Ext4 case insensitive. So the basic idea that we can do now is we go to the super block, which is the first block in your disk where you have all the information on the file system, and you store the encoding information that you want, like the version and which encoding is that. And then you configure each inode using inode attributes, which is just flags of each inode in your file system, to say that that directory is case folding or not. So now you can have case folding per directory. Cool. The directory needs to be empty before changing this attribute, because if it's not, two files that had the same name only differing by case, if you make that directory case folding, it collides, you don't know which one to return. So we follow the same implementation done as fscript, for instance, for encryption. The directory needs to be empty, or I'm rejecting your request. And then we just go to the Ext4 compare the entries and change str compare to UCD str case compare if the directory is case folded, and we are done. Thank you very much, except that it doesn't work. So Ext4 has this very cool feature for very large directories, but it's actually enabled for like directories of over a few files, which is it doesn't perform a linear search on the directory entries in compare one by one. It calculates the hash of the file name, and it performs a lookup, and the directory entry list becomes a lookup table. But the hash of hello in uppercase and the hash of hello in lowercase are not the same. So we are not able to find our files anymore, unless we change the hash. Now we define, this is very easy to solve, we define a new hashing solution, a new hashing function that calculates the hash of the normalized case-folded function. Really cool, but now the layout on the disk changed. So now I cannot take your current file system that you already have and make it case insensitive. You need to recreate your file system. Sorry. And this is something I really wanted to avoid, but there is no way around this. The performance, though, is terrible, because we have a functionality in the kernel called the dcache, which is quite important according to this guy called Torvalds. It's just it's a cache where you store your entries that were looked up before because you believe they are going to be looked up after, right? You always do an ls before copying something. So we store the entries there. But you cannot find the entries because it's a hash table, the hash is different, etc., etc. So let's use the same solution. Hash is now the hash of the normalized case-folded version. It's okay, we can do that. We just use these two hooks to implement the new hashing mechanism in VFS, and we broke something called overlay FS, which is something that lies on top of your file system, because they make use of those things as well. And this is a pain to change. But okay, we can live with that because, come on guys, we are doing case-insensitive, it's hard, we are not gonna fix everything at once. So let's commit that. But negative entries cannot be trusted anymore. And turns out that negative entries are important. Negative entries are the entries stored in the cache that tell you that a file does not exist. So every time you look up for a file, you do a cat hello world and hello world has been removed, it adds an entry there saying, oh, there is no hello world in the disk. And this is cool because going to the disk every time and looking through the entire directory is very costly. So negative entries are essential for performance. In particular, if you start any program, it tries to load several libraries, most of them which are not there, thanks libc. And now if you don't have negative entries, loading any program is super slow again. So we need to support negative entries. Let's just try to make it work. Let's test this scenario. I touch a directory, I create a file in a directory with uppercase A, I remove this directory, everything in the directory, so now I have a negative entry A uppercase. I make my directory case-insensitive and I created a lowercase a, and the file gets created as A uppercase. So my file system is not disk preserving anymore. That's a bug. And the bug is not in the Ext4, it's in the VFS. My entry was removed, but when I try to recreate the entry with a different name, it uses the old version. So I cannot trust negative entries. There are two solutions for this. Well, screw negative entries, I don't need them. And that's what the XFS people do. If you enable case folding in the XFS, they don't store negative entries anymore, but they can, because they have a lot of B-trees, they cache a lot of stuff in the kernel, so they have good performance. Ext4 doesn't. There is a proper fix for this, which is invalidating when changing from negative to positive. So after I remove my file, if I recreate it, I don't reuse the entry. So, good. It's a bit tricky, it's doable, there is some issues with making the maintainers accept it, but we are getting there. There is another problem with encryption, which is, well, we have, how do we solve file names that are encrypted? Well, we can just the current lookup, it compares the entry to the encrypted version of the string. That doesn't work because encrypting one version is not the encrypting lowercase is not the same as encrypting uppercase. Let's try the same hash solution. We can't, because now we are performing the comparison, but this means that the hash that we modify on disk changes the file name. So this is not only not disk preserving, but now every file you created, we change the name of it in the file system. And that's terrible. Another solution, let's decrypt the entries and compare one by one. The performance sucks, but it works. There is another fast but broken solution that I was trying to get, which is store the actual file system as an X attribute, an extended attribute, so we don't store it in the space for the file name, we store it in the inode, but that also sucks because now for every lookup we need to get the inode, which we don't do right now. And getDents, which just returns a huge list of the entries. Now it needs to get the inode of everyone, or it just returns the encoded version, which is completely useless. So this doesn't work. Anyway, just the status of where we are right now. We did a lot of things, we have a lot of things merged, and we have some problems to fix. So basically, we have all the support to use this feature right now merged in 5.2 and already released. The Unicode subsystem, the UTF-8 database, and the Ext4 support, they are all there. Support for E2FS programs, which includes MKFS, FSCK, change CH attribute, which allows you to enable the feature. They are all available for everyone to use on 5.2. We implemented a very interesting optimization of caching the case-folded version at the Ext4 level on 5.3, so now lookups are way faster. Our work in progress right now is fixing the dentry cache, the negative dentry problem, is splitting the database to a module, so if you don't care about case-insensitive, you don't need to load those 90 Ks in the kernel. We need to finish to fix FS-script support and avoid using the VFS hooks because they are evil. If I use them, I break overlay FS. Future work, and this is really cool. I want to make everyone stop using these hooks because they are problematic. And this will fix FS-script also with overlay FS. We also want to support more file systems. I started to implement this on Btrfs, but it's still ongoing. And we want ways to optimize the FS-script lookup support. And finally, bring the cache that we added on the Ext4 to avoid multiple case foldings of the same string and bring it to the D cache. And when we do that, the D cache will act as fast as a lookup for case-insensitive on a file that is already cached will be as fast or almost as fast as the lookup of a case-sensitive file system on Linux. This is it. Thank you. Okay.
So, there is time if anyone wants to ask you something.
Gabriel, it's impressive work, really, and the traits of perseverance are remarkable. So I'd like to ask you, because I remember we talking about this more than a few days ago in a bar, and I want to ask you, how long did it take, to get it finally merged in 5.2? And I think it's a good tip for others in the value of not giving up.
To implement the code,
No.
basically
Everything.
a month.
No,
To get it merged, 2 years. And the most important part of the work was going to conferences, speaking to people, giving presentations about this, and slowly convincing at each level of the maintainer chain until we got to Linus Torvalds back in November, and he said no. The design was a bit different by then. We didn't have the Unicode subsystem. We used NLS, which is another chart set subsystem in the kernel that is a bit limited. And he said, no, you cannot use NLS because that is crappy code. We just need to rewrite it from scratch. So back in November, we rewrote it to use this new subsystem. And then he didn't oppose it anymore. He was happy with it, and it got merged after exactly 2 years since I started this.
Very cool. And another question, I think I read in the Linux Weekly News entry that you changed the normalization, usage.
From the...
I think on V6.
From the final iteration, from one before the final iteration to the last iteration of the patch, yeah. So,
why?
Yeah, so we were using the K form, which converts 2 to 5 to 25. Because there are other cases that it solves better, for instance, the office case. And I believe that ligature were more important than simplifying fractions and other cases. But what we really care, what we care the most is compatibility with Windows and Mac, which is terrible because Windows uses one and Mac uses the other. So it was just a political decision. We have good reasons to go to one, good reasons to go to the other. The group that does Samba really wanted C. So we changed it to C.
All right, thank you.
Hey, Krisman.
Hey.
Maybe a new question. Why Ext4 and not another file system?
So we want to get there, but Ext4 is a native Linux file system, and this is the one that is most used, particularly for Debian, which is very important for me personally. So I just started there, but the plan is to get to everyone in time.
Okay, thank you.
So in, I don't know, 50 years?
Yeah, depending on how much time you get to get your stuff upstream.
Yep.
Anyone? So, thank you, Gabriel.
Okay, thank you.